calculate if you are having a distribution of charge, let's say you are having a static electric field and you ask the question how much energy is stored in that field. So let's try to calculate that energy. Okay. So we know, let's take the entire electromagnetic field. So you are having this much of energy. Okay, where integration is over the entire space. Okay. So since we are in the electrostatic domain, E is equal to 0. So what is the amount of energy? So it will be simply, let's call, you can call U E, let me write it simply. So it is 1 by 8 pi E square. So this is the amount of energy stored in the electric field. Okay, E square, it is the magnitude square of the field. Okay. So let's rewrite it. Let's put this kind of, let's try to interpret this kind of equation. For that matter, what we will do, we will convert this equation into the potential form. Instead of writing the electric field, we will just convert this formula to the potentials. Okay, so let's try it. I can write this very. Yes. So you are having dV. I can write this as simply E dot dV. Can I write it? So E dot E is E square. So this I can write as dV. So let's use for 1E, let me write minus del of phi. Okay. For the electrostatic field, I can write. Why can't you go here? Because it's not visible for you. So you can write it in this way. So how much is that? 1 by 8 pi integral dV. So it is E dot Laplace pi. Okay. So it's a simple form. Just rewriting the formula. Okay. So now let's convert this very term into the total. Derivative. Okay. So let's convert this into the total derivative like this way. So you take the divergence of E phi. How much is that? Can anybody? So it is E dot nabla phi, then plus phi into divergence of E. Clear? So now let's use it back. So what I need, I repair this very term. Okay, so this I can write as minus 1 by 8 pi integral dV. So for this E dot nabla, so I can write divergence of E phi, okay, then minus phi into divergence of. Can I write it? It's simple. So what is divergence of E? So it is equal to 4 pi rho. Clear? So this is simply the Gauss law. So del dot E is equal to 4 pi rho. So I have this very formula again, minus 1 by 8 pi integral dV, okay, divergence of E phi, okay, then plus 1 by 8 pi, sorry, since there is a 4 pi here, so 4 pi will cancel with this, 4 pi, so 1 by 2 remains there, so it's simply half integral dV rho times phi, is it? So rho is the charge density and phi is the potential. Clear? So phi is the potential created by the charges in a given region. What kind of charges? So it is the charges for which the density is rho. Okay? So you are having a charge distribution or the charge density rho that creates this kind of potential phi. Yeah? So we'll try to interpret this kind of result in a moment. Okay? So now let's convert this very integral into the surface integral by Gauss divergence theorem. So I can write this integral over some surface. Okay. So this is an integral over y volume del dot some vector. So it will be simply E phi, okay, dot of ds plus half of dv rho d phi. Now what about this very term? So if my boundary, since I am integrating over the entire space, so we are assuming there are no charges at the boundary, is it? So in other words, the field is vanishes at the boundary, okay? So that means this very term vanishes at boundary. Okay, so what is our energy? So this is, in other words, this is the potential energy stored in the field in terms of charge density and the scalar potential phi. Okay? Got it? Okay, so now let's take the point charges. So I have considered here the distribution having the density rho. Let's consider the point charges. Okay, which are situated at, okay, let's consider it this way for point charges. Okay, so I'll write this rho of r like this way, summation of A, and Q is the amount of charge, okay, eighth charge, okay, which is situated at some radius vector RA. You can write this way. Okay, RA is the position vector of the eighth charge. Okay, so now let's substitute it there. So therefore this U is equal to half of summation of dV. Okay, let's write rho of R, phi of R. Okay, so what is this potential? So let's run. So it is dV summation of A QA delta R minus RA. Let me forget the vector notation. Okay, whenever it is necessary, I will put that. So how much is that? Half of summation of A QA. Let's write this as phi A. Yeah? So phi A. So you integrate over volume. So R will be replaced by RA. Yeah? So that means phi of RA I have written as what? Phi A. Clear? So much more. So phi A is the potential created by all the charges at some point RA. Clear? So much more. So this is the potential energy stored in a distribution of the charges. Okay. So let's try to let's try to apply this very result. So there is one subtlety in this result. So that's why we need to apply it here. Okay. So I am having this very result at hand. So have you seen this result somewhere else? Have you seen this? So it is the amount of work done in bringing a charge in a given potential. Is that true? So what is the work done equal to? Let's say if you are having, let's say in some region potential is given, and you are asked to bring some charge at a certain distance in the given field. Okay, how much is that? So it will be the charge multiplied by the potential in that region. Clear? So much on? So you can think this is simply the work done on. Okay, clear? So this is the amount of work done in bringing the charge QA, okay, into the field due to the other charges, okay, at that very point. Clear? Got it? So we'll see it in a moment. Now let's apply. Okay, here phi is. Let's try to understand this result for a. Let's take a point particle for the time being. So for example, point particle at hand is the electron. Okay, let's take electron as the point particle and apply this very result to the electron. Okay, what does it mean? So applying this result to the electron, what does it mean? Anybody? So what I need? Okay, let's calculate what is the amount of energy stored in the field of the electron. Since electron carries a charge, so it will create a field around itself. Okay, so let's try to calculate what is the amount of energy stored in that very field. Clear? So how much will be that? So you multiply, so energy, so you multiply it, okay. So you are having E as a charge, multiply it by some potential, okay. And this potential is created by the electron itself. Let's say you are having an electron here, it's a point particle it carries a charge E. So let's take this as a finite extension. Okay, so it is certain region where you can experience its field. Clear? Got it? Okay, so you will be having a potential defined in this kind of region. Okay, so what is the amount of energy? So that is simply the work done. Or in other words, you multiply E with pi. Okay, let's say this region is R. Let's take this as R. Okay, let's call this region as R. So how much is that? So it is E square by, let's write R naught. Okay, so this is the amount of energy stored within the field of where? In the field, okay, in the region, in the vicinity of the electron. Clear? Okay. So now let's say if this R naught is the radius of this electron. Okay, instead of let's say if this R naught is it is in the infinitesimal neighborhood of this very electron. So that means it's essentially the size of the electron. Clear? So when I am having the size of electron, what I will see? I will see the physical mass of the electron. I should see, is it? Is that true? On that very mass, so I am having the charge is glued on that mass. Okay? Okay, so what theory of relativity predicts? Okay, let's put it this way. So theory of relativity says if you are having a point particle, okay, it always says if you are having an elementary particle, it should be a point particle. Okay, it should be having a zero extension at least, or very small extension, so that there will be no relative effects. Okay, so theory of relativity predicts this electron has to be actually a point particle. So if it is a point particle, that means this R naught tends to 0. Is that true? So that means I am looking the energy concentrated at the point itself. Is it? So how much is that? So in that case, this U tends to infinity. Okay. So that means you can call this potential energy as a self potential energy because it is created within the vicinity of the electron. Is it? Or by the electron itself, or it is the amount you can think this is the work done by the electron on itself. Clear? So in that sense we call it as a self potential energy, or you can think this is a self energy of the electron derived from the classical electrodynamics. Clear? Okay, so because of the relativity, it says electron has to be a point particle. Okay, it should have a zero extension. So that means the self energy blows up. So it goes to infinity. So if the self energy, because we know from the relativity, energy is equivalent to mass, is it? So that means the mass of the electron has to be infinite. So classical electrodynamics predicts me what? The electron mass has to be what? Infinite. Okay? So because the self energy is infinite, it implies the what? Mass of the electron should be infinite. Okay, what kind of mass I am calculating here? I am calculating actually what we call as the electromagnetic mass. Okay, let me point, I will discuss this in the later lectures. So let me put it this way. How we define the mass of the particle, simple particle in Newtonian mechanics. So if you are having, if you accelerate a particle or some way, so you are having a particle that carries the momentum p, okay, and that momentum p is actually related to the velocity linearly, is it? P is proportional to v, okay, and the proportionality constant turns out to be mass of the particle. Okay, now if you know in the electromagnetic field, I can accelerate the, let's say, the charge, is it? You got, mechanically you can, let's say P is equal to mv, it is something mechanical. Clear? You accelerate the particle, you give particle the momentum, and you will observe the mass. Clear? The coefficient of the linear velocity gives you always the mass. Okay, in the same analogy, let's put it this way. You are having, let's say, particle carries the momentum. Since we have seen from the conservation laws, if you remember this kind of formula last time, so we are having change in momentum, okay? If you remember that P0 nu ds nu, what was that equal to? Minus, that's over some surface integral Tij some dsj, is it? You remember that? So what we interpreted this as the momentum carried by the electromagnetic field. Okay, so this is actually the rate of change of momentum. If you are having rate of change of momentum, it means the force, is it? So what force is usually? So it's some mass times acceleration. Let's put it in this crude analogy, is it? So that means it should give rise to a mass, but that mass is due to some electromagnetic phenomenon. Clear? So somehow we call that kind of mass as electromagnetic mass. Huh? Got it? So I will discuss it in detail in the last chapter. Okay? So that means if I'm, okay, so this is the concept of the electromagnetic mass. So if I'm saying, let's say you are having the cell of energy, for an electron it blows up, it goes to infinity. In other words, we are not actually able to understand where the mass of the electron, from the classical electrodynamics point of view, whether the mass of electron is purely electromagnetic in nature or something else. Clear? You got my point? Okay, let's put it this way. How we calculate the mass in a given situation of a particle? How we probe a particle? Okay, you have done some sort of solid state physics, is it? Let me start with some example from solid state physics. Suppose if you are in solids, an electron. So it's a very crude example, a rough example you can take. So you are an electron. So when you look in a given crystal, an electron, it's not the electron what you know. It's something, an effective particle. Okay? Because it is surrounded by the potential, okay, or the Let's distortions. This electron always comes with the phonons that are existing in the LEDs, is it? So it's actually an effective particle. What you make, that means when you are probing the electron, okay, by certain measures, okay, or by certain means, so what you see, you are not seeing an electron, you are seeing actually an effective particle, is it? So the mass, what you will calculate from that very measurement, let's say, you will get an effective mass of the particle, is it? Okay? Similarly, let's say if I am having some experiment and I am trying to calculate the mass or try to figure out the electron, is it? So what you need a high energy particle, let's say a charged particle. When it comes near to the electron, what happens? Okay? So there is an interaction between the particle and electromagnetic interaction, and that interaction we describe by some emission of the photons, okay? So this electron will not be the simple electron, so it will be clothed by the photons, a photon cloud. The way you are having electron in solid as a electron surrounded by a phonon cloud, okay? So that means you will not be able to actually penetrate deep into its field, okay? So what you will see, or the mass what you will see, you can think that as an electromagnetic mass because you are probing the structure by electromagnetic means. Got it? So this is a crude way to understand this kind of concept. Correct? You got this point? Huh? So now let's put, in other words, let's put this whole argument in this way. So if I am having an electron at rest, let's say, how much energy it possesses? A rest mass energy, is it? Clear? So now if I try to calculate, let's say, this electromagnetic energy in the electron, okay, or within the field of the electron, so that energy should be actually of the same order as the rest mass energy. If I am trying to get the finite results. Samajh? So what I mean to say, let's say you are having the rest mass energy as mc square, so that should be actually comparable to what? So this energy. You got my point? So this is actually the potential energy. So I am saying this should be same as how much? The rest mass energy. Clear? Instead of below, I am considering this R naught some finite value. I am considering some finite extent. I am saying this much of energy should be of the same order. What? Okay. So what it will give me? So it gives me R naught. Is it? So how much is that? MC square. So this R naught is actually, so that means from classical electrodynamics point of view, we are not able to go beyond this kind of radius. Okay, you can think, okay, So you can think this as the limit of applicability of classical electrodynamics to the electron itself. Samajh? If you go beyond this radius, okay, E square by mc square, okay, this much of radius, so then quantum effects emerge. Okay, so for a given electron, let's say the field produced by the electron, so classical electrodynamics give you valid results only till this kind. So this is actually the finite extension, is it? Samajh? You got my point? Samajh? Now you can observe from here the infinite concept. So since charge is fixed, so if I have to make this R not equal to 0, what it means? So mc square should, this energy should be infinite in nature. Samajh? Okay. So that means the formula what we are having here. Okay, now let's go to the formula back. Okay. So you are having this very formula. So it means this formula contains two terms, is it? So what are those two terms? So it means it contains the energy for a part, okay, in the vicinity of the particle itself, okay, and the energy in bringing the other particles in its vicinity. You got my point? So let's say if you are having a distribution of charge, let's say, so you are having all these charges. So this very formula contains what is the self energy of this particle, the individual self energies, and it contains what is the amount of energy required to bring this particle here in this very region. Clear? So what we will be doing, we will be actually excluding the self energy part. So we will write, okay, so this U contains actually two terms, U1 plus, let's say, U prime, let's say U self energy. So we will discard this. So what will be this U prime? It will be some half, let's say, A, QA, okay? So let me write this as some phi A prime. Okay, so phi A prime is actually the potential due to all other charges, okay, except the charge on itself. Got it? Okay, so let's write it this way. Let's write this resultant, what it means. So this phi A prime means, okay, so it means the potential due to, let's say, some charges QB, let's write some RAB. RAB means the distance between Ath charge and Bth charge. Okay, so let's sum over B. And B is not equal to what? A. Clear? So what it means? So Q by R is the potential due to a charge. So it means potential due to the charges, let's say B charges on the A charge. It excludes the term where A is equal to B. So that means the energy, the self energy term. Clear? So in other words, this U prime is equal to half of summation of A over AB, where A is not equal to B. So QA, QB divided by RE. Clear? Got it? Okay, so now let's take if you are having two electrons or two particles carrying charge QA, Q1 and Q2. Let's say you are having two charges carrying. Okay, what is the energy of this very system? So let's write. So it is half of. Okay, you write first charge. What is the potential? Okay, experienced by this charge due to this. So what that will be? Okay, so you write, let's say Q2, the potential due to this very charge. So it is Q1 by R12. Let's write this is R12. Okay, plus then you see the other way around. Q1, Q2 divided by R21. Since R21 and R12 they are the same, is it? So how much is that? So it's simply Q1, Q2 by R12. So this is the potential energy or the interaction and electrostatic interaction between the two charges. Clear? Got it? Okay, so let's rewrite, reinterpret this result. I mean this kind of result. Okay. Any question? Okay, suppose I give you a system of charges and ask a question So how much energy or how much work done is required to put it in a given, configuration. Clear? So let's say you are having a system of charges and you pose a question. So how much energy it is required or how much work done it takes to assemble a given configuration. Clear? So let's say you are having, let's take the point charges. You are having, let's say Q1, Q2, let's say Q3, let's call Q4. Okay? So you put it in this assembler. You assemble it in this way. Now how much energy it takes? So this will give the interpretation of this result. So how you do it? So you take first charge Q1. Let's take charge Q1. Okay? Ignore all other charges. So does this charge experience any field? No. So that means you can put the charge Q1 at arbitrary point. Okay? So and it requires you no work. So now, okay. So for charge, ignoring all others. So it means you need no work. Clear? So you can put, let's say you put a charge Q1. Let's write, you put a charge Q1 here. Okay? Suppose you are having how many? Q1, Q2, Q3, Q4 and so on. Okay, now let's bring charge Q2. Let's bring charge Q2. So if I bring the charge Q2 in this very region, let's call this Q2. So this is the distance R12 between two charges. How much work I require? I require the work done. Let's say W12. So that will be charge multiplied by the potential due to the first charge, is it? So that is Q2. So it is Q1 by R12. Clear? So this is the potential energy required to assemble two charges. Okay. Now let's take the third charge. Okay. Let's take charge Q3. What is the work done? Now let's call this as, okay, let's write this as W2. Let's call this as W3. Okay. What is the charge? What is the work done? So it is charge multiplied by the potential due to the two charges, is it? So that means what is the potential? So let's write it as Q1. So I bring a charge, let's say Q3 here. So let's call this as R13. So this is what? R23. So I need to multiply it by the potential due to other two charges. So what is that? Q1 by R13 plus Q2 by R2. So how much is that? So Q3 Q1 divided by R13 plus Q3 Q2 divided by R. Clear? So now let's take the fourth charge. Okay, so this is just, I'm counting step by step. So then we need to calculate the total work done. Okay, so this is just the work done for the third charge. Let's bring the charge Q4. So how much work I require? So you take a charge Q4 and multiply it by the potential due to the three charges. Okay, let's take your hand Q4 here. So it is at some distance, let's say R14, R234, let's say R24. Clear? So let's multiply it. So it's Q1 by R14 plus Q2 divided by R24 plus Q3 divided by R34. Where this Rij means a distance between the two charges, I and jth charge. Clear? So now let's take how much is the total work done? So let's take total work done. So that's actually the energy stored in the system, is it? Clear? So that is the potential energy stored in the configuration. So how much is that? You add all these terms. So it is something Q1, Q2 divided by R12 plus Q1, Q3 divided by R13 plus Q1, Q4 divided by R14 plus Q2, Q3 divided by So in general, if you are having n number of charges, so in assembling that, so how much energy you require? So you require something, let's say Qi, Qj, and what is the distance between the two? So let's call that as Ij, and sum over I and j, where I is not equal to j. Is that true? Sorry, so I should write like this way. So you are having, let's say, sum over I, sum over j, Qi, Qj by Rij. Now if you see, so first is the ith index, ith component I, and second is j, is it? But this j is actually greater than I, is it? So you are having, okay, Qi, Qj, 2 is greater than 1, 3 is greater than, I can put this like j is greater than 1. Got it? So in other words, okay, so I'm considering, okay, now look here, I can write here Q2, Q1 as well, is it? Q1, Q2 plus Q2, Q1, they are the same thing, is it? Is that true? So what I will do, I will allow the double counting. Double counting means you write, let's say, Q1, Q2, same as what? Q2, Q1. So I will allow both the terms, Q1 and Q2. So I will get the double number of terms. So for that matter, I will just divide by 2 and sum over all I and j. Qi, Qj divided by Rij, while I is not equal to j. Clear? So the formula what we already derived, so it means it how much energy you require to assemble a given system of charge in a given configuration. Clear? Got it? Any question? Let's consider a distribution of charges and try to calculate the field at a far off point. Okay, let's say you are having a point P. Okay, you are having this is a given system of charges. Let's say you are having some QA at some position RA. Let's take a coordinate system. Okay, so the position vector of this is RA. And position vector where we are trying to calculate, let's call this as R. So let's call this as R naught. So what is that equal to? R minus I. Let's write this way. Let's write this as R naught. Okay, what is this? R naught minus R. So you are given a system of charges which contains, let's say, n number of charges, or this can be a continuous distribution of charge. It can be anything. Okay. So let's try to calculate the field at point P. Okay. So the distance. So we are calculating the field at the distance larger than the distance between the charges. So much more. So we are interested in calculating the field at the distance larger than R. Okay? So we have already encountered this kind of example when we are trying to calculate the electric field due to a spherical shell, is it? So when you look at the far off place at the shell, how it looks like? So it looks like a point charge. Now the question is there anything more to that? So that was a spherically symmetric object. Now if you are having a non-spherical object, so does it always look a point charge? Let's say you are having a system of charges, okay, while the net charge in the system is 0. Okay, how it looks like at a far off distance? Now let me give you a simple example where the net charge is 0. You know the dipole? Is it what is the net charge in the system? So I am considering the symmetric dipole where you are having the equal negative and equal positive charge. Is it? What is the net charge? So net charge is 0, still you get what? Electric field, is it? You still get the potential as well as you get the electric field. Clear? So sure? But let's say if you are having a more general charge distribution, let's assume where dipole moment is 0, where let's say net charge is 0, how it will look like? What kind of field it produces? You are having certain system of charges. Samajh? Now think of a nucleus. Let's give an example of a nucleus. So if you are having a spherical shaped nucleus, okay. So what about that? So you are having only a total charge on that, is it? So now if you distort the nucleus, okay, let's say it becomes oblate or prolate, is it? So what kind of field it generates? You got my point? Samajh? Okay, how the field, if the observer is sitting far away from that kind of distribution, how the field looks like? Let's try to understand that kind of thing. So technically this kind of analysis is known as multiple expansion. We are doing the multiple expansion of a given charge distribution. Okay. So now let's start with the simple at the point P. Okay, what is the potential at point P? Okay, so what is that? So let's try. So it is simply sum over A QA divided by magnitude of R naught minus R. Clear? So is this the potential? So because I am considering the system of charge, that's why I have put a sum. So how to evaluate it? Okay. So since I am interested in R naught larger than RA, is it? So I will use a Taylor series expansion. Let's say apply. Taylor series expansion. Suppose if you are having a function f of R naught minus R, let's say, clear? Let's say, or rather I will take the magnitudes. So you can take the magnitude. Let's write, okay, this way. So write the Taylor series expansion about R naught. So how it looks like? So it is sum f of R naught. Then there is a minus. So you put some R dot gradient of what? Tell me. F of gradient of f that's evaluated at R naught, is it? So let's write that is f of R naught, then plus 1 by 2. Okay. So then there is a x square term, is it? So but you are having, let me write that in this way. So you are having xa. Let's say xa is the component of R. Let's write it is the component of what? This vector R. And let's call this capital XA is the component of capital R. This R. Clear? So then I am having this kind of object derivative of partial XA, partial XB acting on this f of R. Clear? So is this the expansion? So you can equally write this object as, so this you can write simply as XA partial by partial this capital A acting on f of R. So this is simply the Taylor series expansion where the summation over the repeated index is implied. Clear? So there is a summation convention implied on A and D. Do you know this formula? This simple Taylor series expansion. Okay. So now let's restrict our, okay, so therefore I can write, so what is the function of R naught minus R? So it's 1 divided by this object, is it? So Samajh? Is it, what is the function? What is f of R naught minus R? It's 1 divided by R naught minus RA, is it? Okay, so let's write it. So therefore I can write this phi as f of R naught. So it is summation over A. QA will be there. Okay, so f of R naught. So f of R naught minus R. So that's actually equal to 1 divided by magnitude of R naught minus R. Is it? Is that true? So what is that? So it will be simply R naught. Then I am having there is, okay, let me put this way. So then I am having RA. RA means the radius vector or the position vector of the eighth charge dot nebula. Okay. So this nebula is with respect to what? R naught. Let's put as R naught here. So it is a differentiation with respect to R naught. Okay. So it's 1 by R naught. Then let me write half of. Okay. So then you are having this XA. So there is a charge multiplying every term. So let's try. So you are having charge QE, that is outside. B partial 2 by partial XA partial XB. So it's 1 by. So let's write approximately. So I'm truncating it to the second order term. Clear? Any question? So now let's take step by step term. Okay. So this I can write as in this way. So this phi can be written as a zeroth order term plus a first order term plus a second order term plus so on. What is the zeroth order term? Let's take the zeroth order term, which we call as a monopole term. Okay. So that's actually equal to summation of A QA by R naught. So that's actually equal to like this thing, summation over A QA by R naught. What is summation over QA? So let's call that as a total charge Q by R. So Q is equal to total charge. Okay, now forget about all higher order terms. So if you look at the distribution from larger distances, it looks what? Q by R naught, is it? So let's forget over all other higher order terms. So the distribution of the charge in the lowest approximation looks what? As a point charge. So whatsoever distribution you are having at hand, when you look it at a far off place or a far off distance, okay, or sufficiently larger distance, you will always find it looking as a point charge in the lowest approximation. The summation of lowest approximation is the zeroth order approximation. Clear? Okay, now what is the next contribution? It's not only the point charge. What is the next contribution? That comes, so that is this phi 1. So now let's write phi 1. So what is our phi 1? It's minus summation over A QA RA dot of nebula of 1 by R naught. Clear? So this is the potential due to the next term. Clear? So now let's write. So we write, okay, so a quantity, so D as summation over A QA RA. So this is actually a vector. Okay, so this we call as a dipole moment. Okay, so this is the dipole moment due to the system of charges. Clear? Okay, so what it means? So it means my potential phi 1, so that's equal to minus, so you can write it as a D. So this is actually the potential due to the, so you can think in the, okay, the first order correction to this very field looks like as what? As a dipole contribution. So let's assume if the total charge is 0 in the system, okay? Let's forget everything. Let's assume total charge in the system is 0. What is the dominant contribution coming from? Dominant contribution is with this very term, is it? Let's ignore higher order terms. I'll consider only these two terms, and I am saying total charge is 0. Okay, so that means it will not look like point charge. So this phi 0 goes to 0, is it? So what name is there? Phi 1. So that means at a larger distance, if the total charge in the system is 0, so it looks like as a dipole. So that's what exactly you are saying. So the usual dipole you are studying, you consider the two centers of the charges of equal magnitude, is it? So what is the net charge? So it does not look like as a point charge at larger distances, but it looks like a dipole. Clear? So if total charge, let's say, if total charge is 0, okay, then dominant contribution to the field in other words, the system looks like as a dipole. In other words, okay. So now let's take this dipole moment again. So you are having this D as summation of A to A RA. Okay. So what is RA? RA is the position vector defined with respect to certain coordinate system, is it? So I have assumed actually a coordinate system, and I have defined the position vector of all charges like what? RA. Clear? Got it? Okay. So now let's shift my origin. Okay. Let's shift the origin. Okay. So what that means? So this RA position vector will change. So it is something RA prime is equal to, let's say, RA plus some, let's write some unit vector C, some vector C, because A I have already used. Clear? So I have shifted my origin. Once you shift the origin, what will happen to the position vectors? They will shift by that, some amount. Okay. So let's call that amount to be C. So what will happen to the dipole moment? So dipole moment will change like this thing. So that's equal to summation over A Q A. So that will be RA prime. How much is that? Summation of A Q A. What is RA prime? RA plus C. Clear? So since C it does not contain. Okay. So once you shift to the origin, all the actually charge will be shifted by the same amount. Okay. So that's why it will not carry any kind of index. So समझ आया? So it is some summation of A to A R A plus some C times sum over A. What this object is? It is a total charge. Let's call that as Q. Clear? Now if the total charge is 0, if total charge is equal to 0, what happens? So this is actually the dipole moment. Okay, C times Q. Okay. So it means dipole moment in the change of coordinate system where you have changed the origin. So it is same as the previous one. Okay. So that means if in the system total charge is equal to 0, then dipole moment is independent of the origin. Okay. So in your elementary class, when you are trying to calculate the electric field due to a dipole, because the total charge in that dipole is 0, is it? So that's why you don't bother about what is the origin, how you choose the coordinate system, is it? You choose any kind of axis somewhere, okay, and you try to calculate the field, okay? Now if it would have been, let's say, total charge is not 0, one center is larger, let's say you are having larger positive charge and smaller negative charge, it is still a dipole, clear? But the total charge is not equal to 0. In that case, the dipole moment will depend how you choose the origin. Got it? So how you choose a given coordinate system. So that means it will change by some constant. Got it? Okay.
So if we take spherical shell at longer distance, will it look like dipole?
So it may have, it is having a component, but that's very small. Because look, in the case of okay, in spherical shell, although it's there is a spherical symmetry, so you don't consider actually the dipole moment due to that in normal sense. But if you see at a larger distance, dipole moment, this field due to dipole falls up 1 by r naught cube. We will see that it's 1 by r cube type. So when the distance are very large, it drops to 0. So it's essentially negligible. Clear? So it will only arise if you deform a sphere little bit. Okay? So such that you can create the positive and negative charge centers. Got it?
If we now define the system, then observe it at shorter distance.
Yes. So you will have a dipole moment, a dipole contribution in between. Okay. Now, shorter means what? Look. What I mean by these distances. So when you are observing let's say you are having a sphere of some radius r. So you should be observing it at the larger than the radius. You cannot observe within the radius. You got my point? So it should be larger than the radius of the sphere. are larger than the given distribution. Clear? Okay. So, okay, let's assume you are having Q plus as the positive charges, okay, and let's write then you are having some Q minus as the negative. So these are the magnitudes of the positive charge, and this is the magnitude of the negative charge, okay. So let's say RA plus is the center, okay, is the or you can think this is the radius vector of the positive charge or the position vector of the positive charge, and let's write RA minus to be the position vector of negative charge. Clear? So let's write a dipole, this dipole moment. So it will be summation over A, QA plus and RA plus, is it? So it will be the sum of two terms and then minus. So minus is because you are considering the two separate charge centers, positive charge centers and negative charge center. So it is QA minus RA minus. Can I write it in this fashion? Can I write? Huh? So it is simply the sum I have expanded. So this is the positive charge center. This is the contribution due to the positive charge, and this is the contribution due to negative charges. Clear? Okay. So if I write it in this way, summation of A QA plus RA plus divided by summation of A. So let's divide it by the total charge and multiply total positive charge and multiply like this thing, the total positive charge. Is it? And the same thing here. So what it means? Anybody? So here the answer will appear to your question. Okay. So can you tell me what this means? So I have considered this kind of situation. So you are having this as the charge distribution. You consider, let's say, positive charges here, and you consider negative charges here. Clear? Samashyaman? Let's say you separate. There is a, although they can be, all over. So I have just considered these centers. Now if you see, so this will be actually what? Center of mass coordinate of what? So positive charge center. You can think it as, let's say, the positive charge center, and then you can think as what? A negative charge center. Clear? So if you see this actually the center of mass coordinate of what? Positive charges. Let's call it as RA. So I will write it as, let's say, R plus, because it does not depend, A, summation over A QA plus minus R minus summation over A QA minus. So this is actually the, so this will be center of mass coordinate for the positive, or it is from center of the positive charges, is it? So you can consider it as a distribution of the positive charge, their center, and this is the center for what? Negative charges. Clear? Samashavan? So now let's write if the magnitude of, since these are the magnitudes, so QA plus is same as the total charge, positive charge is same as what? Total negative charge. So let's call that as some Q. Clear? So what I am saying, in my system, positive charge and negative charge are same. Clear? So what it will look like? So it is G is equal to R plus some Q minus R minus Q. What is that equal to? R plus minus R minus. I should put actually a vector here, because it's a vector quantity. So what this is? R plus minus R minus. So it is the distance between two charge centers, is it? So let's call this as R plus minus Q. What this is? This is the dipole moment, what you already know.
So
Got it?
Charges are same. Why not R plus and R minus?
No. It is this. Look here. Charges are not. I am saying the total magnitude of the total charge. So this is the total positive charge. I am saying the total positive charge is same as total negative charge, and there is nothing like. So it's actually the average coordinate. Yeah? So you got it? Huh? So this simply gives you the center of mass coordinate of what? Let's say negative charge, and this is the positive charge. Huh? Got it? calculate the electric field. So I have the potential at hand. Let's calculate the electric field. So what is electric field? So it's minus nebula phi. Okay, so it will be field due to dipole. So what is minus? What is phi? Phi 1? What is phi 1? Can you just get it? Okay, so let me. So phi 1 is actually equal to minus d dot nebula of 1 by r naught. How much is that? Minus d dot vector r naught divided by r naught square. Sorry, r naught cube. Huh? Is it? So what is the differentiation of 1 by r naught? So this is the differentiation with respect to r naught. Huh? So what is the differentiation of 1 by r naught? Minus 1 by r square. Is it? So you multiply it by the vector r naught. So because it's a directional derivative, huh? So that's why you put a unit vector. Huh? So therefore, what is the electric field? So it is minus and minus plus gradient of d dot r naught by r naught. So how much is that? So you write it as a gradient of d dot r naught. Okay. So 1 by r naught cube plus gradient of 1 by r naught. Simple differentiation rule. Okay. Then d dot. Clear? So this I will leave as an exercise. Just calculate this gradient of this thing. So it is gradient of a dot d, that we know, and the curl of r naught is 0. Is it? Is it true? Curl of r naught is 0. Curl of d is also 0. You can see it. It is again 0. So there will be only one term which will contain the gradient term. So that will be only the gradient term r naught. So just calculate that. So use that kind of formula. So I will write it as E is equal to, so it will be something 3 into d dot r naught vector into a vector r naught by r naught raised to 5 minus vector d dot r naught. So this is the result. Okay, now I can put this r naught vector as some unit vector r naught, and is a unit vector in the direction of r. Okay, so you can write simply. So you will be having two factors coming here. So d 3 times d dot unit vector n and n unit vector minus this d divided by r naught. So this is the field what you know. So what is the field due to a dipole? What is the field due to a dipole? How much is that? 1 by r cube, is it? So now it contains, because it depends upon the direction how you choose the unit vector. Let's say if you choose the unit vector along the axis of the dipole, okay? So much human. Let's say if it is along the axis, then you will be having some term, and if you choose it, let's say perpendicular to the dipole, you will be having another term. Clear? So much human. So what is that? So the axial is actually twice the larger of what? Perpendicular, is it? So if you take, let's say, the axial part, so you get actually 2 times d. D is the dipole moment divided by r cube. If you take the perpendicular, this will be actually 0, is it? So it will be some d by r naught cube. Clear? So no, it is not equal to 0. So you will simply get what? D by r naught cube. So you need to check it. So this is electric field due to the dipole. So there is another useful formula with which we can calculate electric field. So let me write that. So it's actually equal to electric field. And this thing. So sometimes this is a very useful formula to calculate electric field due to a dipole. Clear? So this is all about the dipole moment. Now let's go to the next term. that's a quick. That we have already done. Okay, so the home assignment for you people will be to calculate the electric field in the in spherical polar coordinates. Let's say. So rather, you have to do it in the cylindrical coordinates. If you see, it is having an axial symmetry. The dipole, is it? So let's say if you are having the two charges. So, do you think there is an axial symmetry? Do you think there is an axial symmetry? What it means, axial symmetry? So if you rotate the dipole along the axis, okay, let's say if you rotate it this way, so about a given axis, dipole moment will remain same, is it? So the field will not change. So that means you are having an axial symmetry, is it? So there will be only two components of the field coming. One will be depending on R, another is theta. So calculate the ER component and E theta component. Clear? समझ में? Or in other words, calculate the dipole electric field due to the dipole in angular coordinates. Huh? So you just need to choose the unit vector. Huh? If you are having an axial symmetry of the system, choose a unit vector. It is very simple to do. Huh? Okay, hint will be you can think n as cos I plus sin I kind of thing. Huh? Okay. So what we have learned here? So it's time for. Huh? Okay, 5.